Chapter 24, our last chapter for the semester. Today we're going to look beyond our solar system. We talked about our solar system the other day and how the sun was the center of it. It's the star that's at the center that pulls all the gravity in. The star is the basis of the solar system. Then you have the solar system. Outside the solar system, you have what's called the galaxy, which is a collection of solar systems and stars. Then, when you combine all the galaxies together, we have what we call the universe. Let's start with looking at stars and look at their properties. We learned that Hipparchus had categorized the stars, 850 of them, by their brightness. Stars' brightness are controlled by three factors: the distance, the temperature, and the size of the star. First, when you're talking about distances, we need to use terms that are easy to understand when we're talking about very large distances. The term light years was described as the distance it takes the light to travel in 1 year. 1 year is about 9.5 trillion kilometers, or 5.8 trillion miles. So obviously a very long distance. Light years make it easier and more simple to talk about outer space properties. The other thing that happens with the distance of a star is what we talked about the other day, which was the stellar parallax. The stellar parallax is the apparent shift in a star's position due to the orbital motion of Earth. Stars that are near Earth have a larger parallax. As they get further away, they don't appear to shift. It's due to the angle that they are as compared to the angle that you're looking from. So when we measure stellar brightness, there's two ways that we can measure it. One is the apparent magnitude, which is viewed from Earth. So how bright is this object as viewed from Earth? Well, we now know that Earth is not the center of the universe or even the solar system. We still tend to make many of our measurements based on Earth's perspective because that's where we live. So with apparent magnitude, you obviously have the sun as being the brightest star. But absolute magnitude is taking a more subjective look at stars' brightness. So looking at how bright it really is. In order to do this, you have to standardize the distance away that you measure an item. The distance that was picked by scientists is 32.6 light years away from the star is used to measure the brightness of it. The next one's the temperature of the star. Stars look different colors based on their temperature. A very hot star actually looks blue. By hot, we mean greater than 30,000 degrees Kelvin. And a cool star looks red, less than 3,000 degrees Kelvin. At first, this might seem odd because often we associate things that are cold with blue and things that are hot with red, but both of these are still pretty hot, even though one is hotter than the other. And actually, if you think to maybe a toaster oven that you have in your house, when you watch the coils light up, they do go from different colors. They start out, with the absence of color, and they usually turn red to yellow, and then later on to a bluish color. Or if you watch flames in a fire, when the flames are really hot, they're blue or almost white. This is the same thing with the stars. The hotter stars are blue because they're just giving off that hotter energy. Stars that appear yellow, such as our own sun, are in between in temperatures. They're usually the middle ground of temperatures, and so they end up showing up as yellow. In order to organize stars that exist in our universe, they've been classified using what's called the idealized Hertzsprung-Russell diagram. This diagram maps out different aspects about the stars, specifically the brightness and the temperature. You'll see on this graph the temperature is along the bottom in Kelvin, so you have very bright stars all the way to the left of the graph, and dimmer stars, or very hot stars, all the way to the left of the graph, and dimmer stars on the right. So in that diagonal line that runs through the middle here, it shows that the cooler stars are red, then you get into the medium stars yellow, and the hotter stars are blue. Then you'll see on the left-hand side of the diagram a luminosity scale. Luminosity just means brightness. The very bright stars are higher up in the luminosity scale, and the dimmer stars are further down. You can see they base this on what our sun actually looks like. So 1 is kind of the standardization here. And our sun is given a score of 1 right in the middle. And then the stars get either brighter or dimmer. The other thing you can notice is on the right-hand side we have what's called the absolute magnitude scale. This scale is based on that distance away that's standardized. And instead of giving numbers based on the sun, they give different numbers. 0 is given right up here, and so 0 is actually at a decently bright star. Then the absolute magnitude, it goes down. Negative stars get a are more bright, so a negative absolute magnitude is a brighter star, whereas dimmer stars, such as down here in the graph, are given positive values, positive 20 and positive 15. So those are two different terms, absolute magnitude and luminosity. We have different life cycles or life stages of stars. Just as people are born, then they go through adolescence and the teenage years, later on they're an adult, and then they're elderly. Stars have kind of life stages too. The life stage that you see on this slide is called the main sequence. These stars are in that main sequence stage. This is where 90% of all the stars exist. This is kind of like your teenage years to maybe when you're 60 or 70. It's just the middle of your life. It's where most of your life is spent. Before this, you were maybe in birth or very young. After this, maybe you'll have a midlife crisis or you end up becoming elderly and eventually passing away. These stars range throughout the spectrum of different degrees of temperature and different degrees of luminosity or brightness. However, in general, their size is small. The next stage after main sequence, I kind of consider it midlife crisis stage, is the giants or the red giants. This is when the stars start to collapse in on each other but are still being pulled out by fusion. They're very bright. As you can see, they're in that the upper portion of the graph that relates to the bright stars, even though they have the negative absolute magnitude scale. If they're really, really large, then they're called supergiants. Because they're bright, they're called red giant. Well, because they're cool, they're called red giants. They have the red color because they're on the right-hand side of the graph. And then because they're big, that's why they're called giants. Stars, there's only a few stars at any given time that are actually in this phase of life. And this phase does not last very long because the energy that's being exposed in it cannot sustain itself for a while. After the red giants, you end up going through the phase called the white dwarfs. And you can see where they're located. You can see these three distinct phases on this diagram. The white dwarfs, as expected, they are light in color. They're also very small. And they're not always white in color, but they're often within that middle temperature ground. So they wouldn't really be very bright red or bright blue, but they would be more that yellow color. And only 10% of stars are in this stage of life. So again, it's a very small amount of stars are in this stage. That main sequence is where they are most of their lives. We also have different types of stars that exist. One type of star is called a binary star. This is when two stars orbit one another. Most stars are actually binary stars that orbit each other, and what happens is they orbit around wherever the center of their mass would add up to. So if you have two stars of equal mass, you end up getting an orbit that they're both following along. If one star is bigger than the other, it almost seems like the smaller star is orbiting the bigger star, but really they're orbiting their center of mass. This is very common, but we kind of don't recognize it as being common because our star is not a binary star. It's a single star that exists. We also have things that are called variable stars. We can have two types. One's a pulsating variable star, so it can change the amount of brightness throughout different times of the year, different days. So in this picture on the top right, you can see that this is the same star being imaged, but on different months it has different luminosities. Sorry for the slight pause. But to move on, you can also see we have eruptive variables. These are stars that are going through an event called a nova. And so you can see in this picture from on the bottom where this star is starting out in May and it's starting to expand and explode. And so this is kind of like a volcano erupting, if you can think of it like that, or a rose blooming. This star is getting larger and larger and larger as forces act within it. Besides having stars in outer space, we also have all this other matter that exists. Often we think of it as empty sky, but when we look at the radiation and the energy coming in from the atmosphere or from the outer space, we can observe there's actually energy out there. Within what we normally think of as empty sky, we can have what's called nebula, or clouds of dust and gases. We have two different types of nebula that exist. One is a bright nebula. Bright nebula basically looks like smoke, as you can see in the picture on the right. The nebula looks like it's glowing, looks like smog. And this really is just occurring because they're very close to a hot star, and it's causing the reflection off of the hot star. Just like clouds at night look black, but clouds that have a reflection, if there's a full moon, you can see the clouds, they look like they're glowing. But if there's no full moon, there's no source of light for them, they just will look black. So the bright nebula is close to a hot star. And dark nebula is like the clouds that are in the sky and there's no moon outside. They're not close to any bright star, and so they look dark. The material that's found in both the bright and the dark nebula contribute to the formation of stars and planets. It's pretty much like dust in our atmosphere, and eventually it'll come together to form some other type of entity. So how do stars go through their different phases? How are they born? How does this nebula start to come together and create this entity called a star? Well, there's actually two opposing forces that are in a star. Gravity within the star acts to contract and pull the forces together, pulling those dust and particles of the nebula into one center point. However, at the same time, there's a process called thermonuclear energy, and this process expands the star and starts to spread it out, so it doesn't just collapse in on itself, but it's also expanding outwards. So that contraction by the gravity, that's the first stage in a star's life. So appropriately, it's called the birth. Next, the stars start to burn and release energy, causing that expansion. And there ends up becoming this balance between the gravity that's pulling in and the energy that's expanding outwards. When this stage exists, we call it a protostar. You can see on this diagram here, still similar to the Hertzsprung-Russell diagram, because you have the temperature on the bottom and the absolute magnitude on the left. And you can see this is showing where the main sequence stars would exist. So you have the nebular or the dust and the gases up here, and then the reaction, the hydrogen burning releases the energy that allows the contraction and the expansion to be in balance, and we get a protostar. Next, that star will go into a main sequence star. And main sequence stars, they exist in that location all along this main sequence here for most of their life. As I said, 90% of the star's life is in the main sequence. So they're here and they age at different rates, just like people age at different rates. Some stars are there for longer, some stars are there for shorter, but they're aging. Eventually, that outer expansion, that hydrogen burning, starts to happen and it outweighs the gravity that's pulling it in. This causes the surface to cool and start to become red. As it becomes red, that means that the temperature is decreasing. And also the core starts to collapse because now gravity is stronger because that outer expansion is not occurring as much. So when the gravity starts to take over and the outer expansion starts to decrease, we end up going into the giant stage, or the red giant, or the supergiant. This is all dependent on how big the star is. Once we're in that supergiant stage, it's not long until the mass of the star is burned out, and we end up resulting in what's called burnout and death. There's different types of deaths that can happen for different masses of stars. If you have an average star, either low or medium mass, that's when the star will collapse on itself and it becomes what's known as the white dwarf, which we already talked about. But when we have a very massive stars just have so much energy, but they also burn out so quickly that they have a short lifespan. They'll burn out in what's called a supernova explosion. Supernova explosion will end up resulting in the interior condensing. As it condenses, we get one of two outcomes, either a neutron star or a black hole. So the remnants of what's left over after a star dies. If a white dwarf is what occurs, as does happen in the low and medium stars, it eventually cools off and becomes what's known as a black dwarf because it's not giving off any color anymore. However, if we had one of those giant stars that ended up bursting in a supernova, we can have what's called a neutron star. This is just when the supernova collapses in on itself. There's a strong magnetic field, but it's not the super intense gravity of a black hole. The first supernova was discovered in 1970 and it's called the Crab Nebula because it basically looks like a crab. When you look at these images, such as the one on the right, remember, this isn't the visible spectrum that you're seeing. Energy in certain wavelengths come into the observers, and then scientists filter them using the visible colors so that we can make out what energy is floating around in the universe. And last but not least is the black hole. The black hole is the result of a collapsed red giant or super red giant that's collapsing in itself as it goes through the supernova. It is so dense that no light escapes. The gravity is so intense that it pulls light inside of it. It becomes so hot, and the only thing that can escape out from a black hole that we know of is X-rays. So in order to actually see a black hole, we end up having to look for areas of high concentrations of X-rays, such as Hubble did. There are some likely candidates that scientists have identified, but they're still not sure about all the aspects of a black hole, as we never have been able to develop anything to send into one. So one is called Cygnus X1, and this is just, scientists are guessing it's there because there's an X-ray source, a very strong X-ray source there. So now if we move outside of stars, we move outside of the solar system, since we already talked about that, we get into what are galaxies. We live in a galaxy called the Milky Way. You can see the Milky Way galaxy late at night in the sky. Kind of looks like it starts to get really cloudy. It's actually strips of the Milky Way galaxy. We know what the galaxy looks like because radio telescopes have received radiation from the galaxy and from entities in the galaxy. From that we know it's a large spiral galaxy and that it has 3 arms. These arms are made up of stars and interstellar matter. Originally, people thought that the sun, our solar system, was in the center of the galaxy. This is because you looked out in every direction and you could see stars equally in every direction. But if you think about walking into a forest, when you get in if you get into a forest that's 200 miles long. Once you're in a mile into the forest and you start to look around, every direction you look will have the same amount of trees. It seems like you're stuck in the middle. But now we know that that's not true. You can see on this picture up top that this is our whole galaxy, the Milky Way. This is the nucleus of the Milky Way, and the sun is actually on one of the arms, sticking out on the side, not near the center. It's actually now hypothesized that the center of our galaxy, and maybe other galaxies, is a black hole. And that gravitational force that's coming from the black hole is what's keeping our galaxy in orbit around the center, here labeled the nucleus. We know we're not the only other galaxy due to things that we've seen out in outer space, such as images from the Hubble Deep Field. Again, you see the picture on the right that has been filtered to show different radiations. First person to actually propose that there might be another galaxy was Immanuel Kant in the 1700s. There are now known to be 4 basic types of galaxies. Spiral galaxies, which is what the Milky Way is, exist, but there's only about 30% of all the galaxies are spiral. Spiral galaxies have both young and old stars. And as I already said, the Milky Way is a spiral galaxy, another one's Andromeda. The other 3 types that exist, and you don't have to know too much about them except for the names of the types, is that there's a barred spiral galaxy, an elliptical galaxy, and then an irregular galaxy. 60% of all galaxies are in the elliptical. And the regular is kind of just a catch-all for the rest of them that don't really fit into a category one way or the other. While you may have your own beliefs about how the world began, how the universe began, whether it be something you heard on TV or in religion, leaving this class, you should be aware of the most widely accepted scientific theory of how the universe began, and that is the Big Bang Theory. This theory accounts for the galaxies being able to move away from each other. The universe was once confined to one area, a small, massive area that has started to expand about 15 billion years ago. As it's expanded, everything has just started to grow further and further away from each other. We don't know if there's other universe out there. We don't know why it's exactly growing. Is there other matter out there that's pulling on it? What is causing the universe to expand? And as it expands, we can no longer define where the center was because it's not like it's growing, but instead it's all stretching out in all directions in every location. It's like cells growing or a loaf of raisin bread expanding. They're not really sure. There might be other universes out there, but for now, all we're going to really concentrate on is the scientific theory for how the universe began. Scientists believe that there might be 2 possibilities. Either the universe can keep expanding forever and ever and ever, or eventually, maybe, the outward expansion will somehow stop, kind of like a rubber band, and get snapped backwards due to gravity, and the whole universe will just fall in on itself. And they've hypothesized that this is all going to be dependent on density. For now, as we'll leave you off with the end of the universe, this is the end of the semester, and just want to point out some things, is that first of all, I know you're not going to remember every detail I taught you. You're not going to remember every terminology or every single process. But there are some things that I hope you leave this course being more aware of. I really hope you look at the world a little differently. I hope you're more willing to ask questions about your actions and things you hear on TV. Questions about the activities that happen in the world. Be more productive on finding your own information out, not just taking what you hear to heart until you do a little bit more research. Be more observant. Pay attention to some of the current events that exist out there. These things are going to affect your future. And, I also hope this class prepared you for the real world. We had a lot of tests, we had a lot of assignments, there was a group project, and all of these things are aspects of the real world that you will have to deal with. When you get a job, you're going to have to be organized. You have to be responsible. You have to start managing time between friends, family, and work. And hopefully, this will have given you some experience in doing that. I wish everyone the best in the future, and thank you all for taking my course. Bye! Hope I see you around someday.